Really quieted you down. I didn't mean to. Stuff's happening. So you guys have any questions from homework stuff, or just general questions, or proclamations, or non sequiturs? Comments? You guys are good? You guys are okay? If you're in WebAssign, somebody finally emailed me to remind me, so I put the next couple sections up in there. Take a look. Anytime you're going in to do homework and it's not there, don't just go, yay, go, oh shit, and email me. Because that's bad. A few more people came in. Anybody not get their test back yet? Okay. Okay. First thing I want to do is just kind of really quickly review what we did last time. I've got a worksheet that I want you guys to work on. It's crazy. I also want to point out that I realized that past Jeff did a great job at the schedule. I don't know if anybody's noticed something, that there's an issue with the next test. Somebody noticed it. It's on the Monday of spring break, which, good job, past Jeff. And I can't put it on the Monday after spring break because I'm not that evil yet.
I thought it was the 26th.
No, so currently on the homework sheet it says the 31st. Yeah.
I think I also have the 26th when I tried.
Really?
Yeah. I believe it says
Oh,
26th.
thank the gods. Neat. Okay. Mine say 31st. That's weird. All right. So if you look on Canvas or whatever you've got, it says.
Yeah, it says March 26th.
Oh, good. Good Lord. I must have a different iteration that I was looking at. Okay, so it's up on Canvas that way?
Yeah.
Thank God. So we're good. We're good. Good Lord. I was probably looking at one of my iterations as I was trying to figure out the schedule. That's better. I always like to showcase my mistakes, but that time I didn't need to. So last time what we got into was the being more specific about the three-dimensional objects we were talking about. So when we talk about three-dimensional objects before chapter 14, they could be anything, So they weren't really functions because they didn't pass any vertical line tests. So for a three-dimensional relationship to be a function, every possible vertical line going through the xy plane must go through it only once. Does that make sense? You guys with me? So if it's 2D, any vertical line would be going through the x-axis, and they can only go through once. Now we got to extend that to the plane, of course. Yes? But it's still the same idea. These vertical lines going through the xy plane, it can only go through the surface once, and then that's a function of x and y. How we doing? This is the whole idea about if I ask you where's the ball 5 seconds after you threw it, and you tell me it's 2 feet up in the air and it's 7 feet up in the air, I am concerned about what has happened to me, to you, to the ball, to the world. You with me? Where's Frank? He's over there and he's over there. What has happened to Frank? Is Frank okay? Are you guys kind of with me? Okay. Maybe he's got the little thing from Harry Potter, you can spin it back, I don't know. Okay. So, one thing we did was we talked about domain of functions, functions of two variables in this case. We discussed a few examples, how to do it, so I've got an example I want you guys to do here in a minute. We then talked about limits, and that's the one I want to focus on because we didn't get very far with that idea. I did some weird things where I was walking around talking about ways to get to a point, and I'm hoping that made some kind of sense. The nice thing about 2D is you're constrained in how you can approach something. So I know in calculus your teacher must have done something like this at some point. You go from this side, you go from that side. Right? Yes? But now, if I have a point, this point right there, my finger, right? I can come at it this way, I can come at it that way. Yes? Okay. So on one level, I think I got through to you guys last time that we're going to focus ourselves on very specific examples, because otherwise, if I just give you a completely random thing, it will drive you insane. You try to think of all the different ways to get there. You guys kind of, okay, a little bit. So, let me see, did I give myself an example? That would be great. Oh, I did. Look at me go. Okay. What are you doing? Okay, here. So here's an example of, yes, beautiful. Let's look at this guy. Now, obviously, where will this guy have some issues? What point? 0, 0. Now, it is true that we very often kind of focus on 0, 0. A different function could very easily have an issue somewhere else, correct? In fact, you could have, let me see if I can push my luck here. Sure. Real quick, don't even write this down. We might talk about something like this at some point. Yeah, this is good. I need to talk about this. Where would this function have an issue? And be careful how you say this. If you say at x equals 1, that doesn't make sense.
When the denominator is 0?
Sure, that's true. Which would lead somebody to say at x equals 1. Well, what's wrong with saying at x equals 1? Because my inputs are points. So my issue should be either a point, but what in this case is the problem? What's wrong with G? Does it have an issue at a point? No. Can somebody give me one point it would have an issue with? 1, 1. Give me another one. 1, 0. So what's the definition of the thing that contains all the points this has an issue at? What's true about every point you just gave me? X equals 1, which we understand to be a line. Yes? So this thing is going to have some weird shit happening at x equals 1. Above, it could be doing this. Like, here's the x equals 1 line. Where's my, there it is. Here's my x equals 1 line. Here's, here, sorry. For some reason, I have to be very precise for this. Here's 0, 0. Here's x equals 1, yes? So maybe that function is going to look like this, yes? Or it could look like this. It's going to have an issue all the way up and down. It's going to do this all the way up and down this line. We'll try to graph this later. I'll keep hold of this. Is everybody sort of with me? You got me? So obviously in 2D, we have x inputs where a function might have an issue. In 3D, we have a point or a collection of points where my function will have an issue. Now, why in f of x, y? And this is, why does this not have an issue at more than one point? What's the only way, sir? They both have to be 0. That's the only way they make the denominator 0, is if they're both 0, yes? Does somebody see a different way to make the denominator 0? Do you see how you can't? The minute either one of them is not 0, there's no way the other one can make it become 0 because they're both positive, correct? You guys see that? Because again, you guys very smartly elected to not let me use complex numbers. Yes? You guys with me? You guys chose that. And that was a good choice, by the way. This class would have been very, very. Alright, let me stop for a second. Are you guys really with me? I wasn't even planning on talking about that, but now I'm like, ooh, that's a good point to make, Jeff. Ooh, thank you. So this guy only has an issue at 0, 0. This guy has an issue with every point where x is 1, and there's an infinite number of those. So he's got a whole freaking valley that he has an issue with, yes? Okay, I love it. I love it. So, I don't think I did this with you last time. I don't really want to, so I'm not going to, because we're going to do something like this later. But just to show you what I could do. So if I want, what do you think I'm going to investigate? And this one I'm going to save for later. We're going to graph this later, and we're going to see how that shows up in the graph. What do you think I'm going to investigate? The limit as x, y goes to? That's right, kids. Let's see. Now, in normal 2D, remember what we did? If I did the limit as x goes to 0, I would let x equal negative 0.5, negative 0.2, negative 0.1, negative 0.01, right? And positive 0.5, positive 0.2. You know, you would approach 0 from both sides. Now, I'm going to do that, same thing, just to cut to the chase a little bit. Negative 0.2, negative 0.1, negative 0.01. Do you see how this is my x's? Yes? Is that cool? And then I'm going to leave a little space, 0.01, 0.1, 0.2. So I'm kind of doing this thing. I'm approaching 0 from both sides, yes? Maybe I will do at least a little bit of this. And then I'm going to let y do the same thing because I'm approaching... Jeff, you can do it, buddy. Can you? That's the question. I think I got it. Yes. Okay. I didn't really mean to put 0 there, but we'll be okay. I'll put 0 there. So I get this grid, which kind of makes sense because I have more than one variable to account for. So without actually filling all of this in, can you guys see how I could start throwing values in for both x and y and filling these in? You guys with me? So back in the day, if we did something like 3.9, 3.99, 4.01, 4.1, and I made a table and I got outputs of 0.98, 0.99, 1.01, 1.1, what would you say the limit is as x goes to 4? 1. It looks like it's trying to be 1, correct? You guys with me?
Yeah.
So you can do something very similar if you make a grid like this. You can kind of see where things are approaching here, yes? How are things are they approaching the same number from all directions? This might you could do. No, I won't. So instead what I want to do is I want to do this. Do you see how I could fill this in and I could see what these numbers kind of are doing, and I could kind of see as I approach, do you see how I could get these diagonals, and if I do this, aren't I approaching 0, 0? And if I do this, I'm approaching 0, 0. Yes? Let's do this. Instead of us sitting here filling this crazy ass grid in, let's look at one the book has already done for us. Yes? Because we're better than that busy work. Here we go. Bodacious. Bodacious. So which function is this? I think, here we go. So f of xy is this business here. Sine blah blah blah. And g of xy is this. Now real quick, do you guys remember the limit as x goes to 0, sine x over x?
1.
Yes, so what would you guess this was going to be? 1. It's kind of like an analog of that in 2D, and I'm sorry, 3D. And then this is this guy. So let's see. They made a table like I was just talking about. And sure enough, if you come at it along, by the way, real quick, if I do this, what path am I taking? Let's see if anybody's with me. If I do this, yeah, what's equal to what if I move along this way? What am I making constant? Yeah, so Rory's perfect. Y equals 0.
I know.
There you go. At least for that reason. Y equals 0 is another name for the x-axis. So a little cheer for you. And then of course if I do this, I'm approaching along the y-axis. I love it. So this is the x-axis and the y-axis. I could come at a diagonal, yes? Do you see what I mean? I need you to see what I mean. If I move my finger along, am I approaching the point 0, 0?
Yes.
Yes. This is the point what? What's my input point here? 1, negative 1. 0.5, negative 5. 0.2, negative 2. And then that would be 0, 0, correct? So this is a very unexciting yet informative display of what I mean by path. There are multiple paths to get to 0, 0, correct? Every single path that we have created is approaching what?
One.
I'm sorry, it's approaching the point 0, 0 in the input. What are the outputs approaching?
One.
They're approaching 1. Every single way I approach, I'm approaching 1, correct? Now this is not a proof, because have I shown you every path I could take? No, but this is a pretty good collection of, if I see this shit for this very simple grid, I feel pretty good that it's 1. Could I be wrong? Yeah. Do I still feel okay about it being 1? Yeah. So we still have to develop better ways. You guys with me? This is good for a first glance. Now, real quick, look at table 2. What's the difference with table 2? And this is for the function without the sign in it. You guys knew the first one was supposed to be 1. We knew that from what you did in Calc 1. This is the one for x squared plus y squared over x squared minus y squared, the other way around?
It's the other way around.
Other way around, thank you. Yeah, that would make more sense. Pick a path to approach. Now what's interesting, look at this path. What's the limit if I go this way? 0. What's the limit if I go this way? 1. What's the limit if I go this way? -1, yes? Do you guys see what I'm saying? This type of thing is really good if the limit does not exist, because I know this limit does not exist. All I need are 2 paths that don't agree. You guys all like it? So let's do this before I do anything else. Let's graph this function and see what's going on. And we'll graph that other function too. So this is the function that they were working with. Oh, poor little guy. Poor little guy. Okay, there you go. This guy. Yes? So I'm going to go over to everybody's favorite little dude, Desmos. I've already got a few open, but can I do it here? Yes, this is nice and clean. Let's see, x squared minus y squared. See if it does it. No, damn it. Divided by x squared plus y squared. Okay. So let's see. One path you could take went to 1, and that was basically coming along. Oh my gosh. Let's see. Sorry. Thank God. Let's see. That was coming along the x-axis. Okay, so let's see if I can show it. This gets a little bit wonky if I try to show you something very specific. But let's see. If I approach along the x-axis, it looks like it's approaching 1. See that? I'm coming down this, I'm right there. It looks like it's going to 1. And just to remind you guys, oh my goodness, multimedia. If I was along the x-axis, y equals 0, it's staying at 1, correct? Okay. If I approach along the the y-axis, it should be -1, correct? Let's see. You can do it, Jeff. Kaboom. Oh my gosh. So, look at the y-axis. See the y-axis? Isn't it -1? Do you see what I mean? So as they approach 0, this is a very trippy image here. But as they approach 0, it depends on what path you take as to what it looks like it's doing. What is it actually doing there? Well, the limit does not exist. It's just an open hole in the middle. Yes? Okay, maybe. I love you guys. How are you doing out there? You doing okay? What's up? Oh God, yeah. Let's all get over that. Today is a day that I wish I didn't have to get out of bed. It would have been beautiful. Today would have been great. And then like all snuggled, and I would be like, it's so cold outside. Watch back. Let me see. Catch up on my shows. Yes. Did you see the last episode of Invincible? I think I'd be sitting there. Oh, look at him. All right. Sorry. That would be fantastic. Yes.
Can you say that again? Why the limit
So, do you agree that if I look, like right here along the x-axis, every point along the x-axis, the output is right here, yes? You with me? So then, as I move along, as I approach 0, 0, it's just staying at 1, yes? Okay. Now, right at 0, can you see, now, it's having trouble, which you should expect, because weird things happen at 0, 0. You with me? But watch what's happening. This is very telling. As I zoom in, watch the area around here. Do you guys see that? Do you see how it's got like a little, it's really having some issues. If I try to zoom in quite a bit, well, let's see, it's really going to have issues. Yeah. Let me come back in. Poor little guy.
I saw it, it's like a funnel.
Yes, so right there, it's like oh man, oh boy, I've really not made this guy's day. Reset, where's the reset?
That's the home button underneath the plus and minus.
This one, there we go, thank you. Okay, that's much better. It is very trippy because it is true that as I go along the y-axis, I'm underneath. Does everybody agree with me? Any point on the y-axis, the output is at -1. Any point along the x-axis, the output is at 1. So at 0, 0, there is this very sudden, jarring, just discontinuity. Yes? So what happens there? I don't know. Weird shit. It is 1 forever. Along the x-axis, the output is 1 until you get to 0, 0. You love it. And it is -1. The output is -1 as you input points that are on the y-axis until you get to 0, 0. Okay. And you guys, we've seen this. What happens if I had a function in 2D where as I approach, let me see, for you guys, as I approach from the left, it's -1, and as I approach from the right, it's 1. What is this? What kind?
Discontinuity.
What kind?
Jump discontinuity.
So there's a jump discontinuity there. It's just kind of happening radially in all directions at the same time. Yes? Is that cool? Trippy. Not intuitive, but it still is analogous to the 2D case. It's just happening in all paths. In fact, did it show me? Sorry guys, let me see. Kind of doing this a little on the fly. Yeah, okay, that's right, I forgot. If you came at a diagonal, let me see if you can see this. Just to really confuse you more, because I don't think I've confused you as much as I can. Yeah, so if I come along a diagonal, look here, right there, this is perfect. Look at that shit. If I come along the diagonal, what are the outputs along this diagonal? Do you guys see what I mean? 0, that's the zeros. And the output, and that's the one that zeros all the way along until you get to 0, 0, in which case there's not just an open hole, it's like it's open and off. Anyway, it's trippy. It's a very trippy function. Let's take a look at let's see. Remember the other one we just created earlier? This guy? What was his issue again? Sorry? Multimedia, I can't take it. This should have something weird happening along the entire x=1 line, yes? All right, let's take a look. I'm doing this live. I have no idea. Let's see. Doing it live. Make it all official. F of xy equals, what was it? 3xy divided by x minus 1. Okay. Yeah, isn't this neat? So let me see if I can show you. Let's do this. Okay, so along the x=1 line, you can see there's a really big issue here. Along the x=1 line, so it's not quite doing what I hoped it would do. If I thought about it, I could probably create one. But do you see how, I need you to see if you guys can really see this. If I just look at it straight on, it's not quite, I don't know if you guys can see how this is kind of asymptotic at x=1. If I can isolate a slice, go ahead.
Extend it to 3D and you'll probably see it.
Yeah. Let's see. Yeah, so if you look straight on, it kind of loses it. But this is asymptotic to that plane everywhere. Thank you. Is that okay? Yes.
Is it like going like this way and that way?
So let's see if we can see. On this side, it's going asymptotic up, yes? And on this side, it's asymptotic down, yes? Kind of with me? So there's like a trough, and I was like, I didn't know if it was going to do this or this, and of course, if I thought about it for a minute, the top is XY, so it's positive, negative in different quadrants. So it kind of does this thing, yes? On different sides of it. So all along x equals 1, all along this line, the output would approach infinity. Which infinity depends on, remember the top is xy. So if I'm in a quadrant of the xy plane, where x and y are the same sign, then it's going to go to positive infinity. You guys with me? If I'm in the quadrant where they're different signs, then this is going to go to negative infinity. But that also depends on which side I'm approaching x minus 1. So let me do one little thing. Sorry, I'm sort of just playing while you're here. Yeah, there we go. Okay. So if I square the bottom, it's going to take out that influence of the sign change on the bottom. So this is kind of nifty. If I can look at the xy plane, okay. So in this quadrant here, x and y are both positive, correct? So if I approach along this side, it should go to positive infinity. And I can't really see it well. I think you guys potentially get what's going on here. Yes? You can definitely see a tear in the image right here. Okay. Okay, maybe. I wasn't sure how that would show up on Desmos, but you can almost see it. Okay. By the way, if you're getting into any chapter and you're not plugging some of the stuff into Desmos, and when you go to Desmos, make sure you go to desmos.com/3D, yes? You can graph whatever the hell function you're working anything with, right? And it might kind of help you see what's going on. Okay. All right, let's take it back down. Stop playing around, Jeff. Now, let's talk about, instead of doing this forever and just really, really hating calculus, let me show you how to just sort of one level of hate. So, let me see. Okay, this is such a trippy idea about how to capture these paths. One thing the grid has going for it is a path is really, you can just see the path. I can just trace the path out with my finger. And you guys kind of followed what I meant. Yes? But making the grid sucks. Okay. So there must be a more abstract way to do this, which means a more algebraic and hopefully quicker way to do this. Yes? So let's say I'm working with the same thing. Well, is it the same thing? No, I haven't written this down. It might be the same. Yes, it is. Yes, it is the same. Same function we had earlier. Yes? So let's talk about what I mean by paths. And by the way, the instructions on this problem would say find two paths with different limits to show that this limit does not exist. So I would tell you straight up, this limit does not exist. Find two paths that don't agree. Yes? Sort of like, how do you show, what's one way to show a limit does not exist in 2 dimensions? You go from the left, you go from the right, they don't agree. Same idea here, except now I need an actually well-defined path. So what the hell does that mean, Jeff? I don't know. Oh yeah, I did. One way I can approach, does everybody agree with me that if y equals mx, where m is any damn m you want except 0, that as x goes to 0, y also goes to 0? You guys agree with me? this is exactly like approaching along the x-axis, the y-axis, x equals 1. I could approach along, in this case, this would be along a diagonal. Are you guys with me? So if I was y equals x, if I said y equals x, that would be like approaching this, yes? Is y equals x at every point that I'm pointing to? Is y equal x? Negative 1 equals negative 1. So this is the line, this is y equals x right here, yes? And if I approach y equals x versus y equals 0, you could do it, Jeff, there it is. Look down here, Jeff. Do those agree? Do those limits agree? No. Okay. So one path I could take is y equals mx. What would how would I use that? If I let y equal mx, what does my function become? First off, I could do this. Because if I do that, don't I have one variable now? And anywhere I see y, I just put mx. Good. So then I get x, m squared x squared over x squared plus m4 x4. Is that cool? And this would be m squared x cubed over x squared plus m4 x4. Yes, limit, blah, blah, blah. Can anyone see what that limit is? Very quickly, without, I mean, you can divide some x's, but who cares? The top degree is, and the bottom degree is 4. So what's the limit? 0. I love it. Well, that would be if it's going to infinity. So let's do this. Limit as x goes to 0. Do you see how I can divide by x squared? And if I let x equal 0, I will get 0. Yes? Let me stop for a minute. How did I get from here to here? I just divided the number of x's everybody had in common, yes? I divided everything by x squared. Is that cool? Okay. And why am I allowed to do that? Because x squared can't be 0, because x can't be 0. Right? I love you guys. What's the only time I'm allowed to divide by x squared? As long as x does not equal. Only time I'm not allowed to divide by x squared is if x is 0. I'm taking a limit as x goes to 0 is x over 0. So I'm allowed to divide by x squared. Now if I let x equal 0, this is 0 over 1 plus 0, 0. Cool. So if I go along that path, I get a 0 outcome. Just like, actually, just like this. If I went along the path y equals x, I get a 0 outcome. Okay. How else could I approach it?
Y equals 0.
Yeah, I could approach along the x-axis, yes? So what happens if I approach along this path? How does this get? So this is path 1, this is path 2. How would I rewrite the function now?
X is equal to y over m.
Sorry? What do I'm letting y equal 0.
It's 0 over x
So it would be 0 over
squared.
x squared, and that's also 0. Damn. Now, real quick, why should you guys have known that already? Because if I let y equal mx for any value of m, the output is 0. So if I let m equal 0, the output is 0. So I don't want to go along the path y equals 3x, because I've already done that. Do you see that? So I've already eliminated every linear path. Bless you. Now, let me stop for a minute. Are you guys starting to get the idea? And again, this is going to be very kind of contained. Otherwise, you can go along a natural law path, or a radical path, or a Euclid path. But we're going to keep it contained. Normally it's gonna be either linear pass or parabolic pass, or it could be y equals 0 versus x equals 0. Yes? You guys see that?
So in this case, if you ever do a y equals mx, you will basically eliminate y equals 0 and x equals 0.
Yeah.
Because they're just
Yep,
functions.
because x equals 1 over my.
So truly, there's no point in ever doing x equals 0, y equals 0.
Well, be careful. The only m that would make x equals 0 for y equals mx would be, because if m is 0, then x is whatever it wants to be. If you want x to be 0, you have to make x 0. So it would be different to travel along x equals 0. That is different from y equals mx. Okay. So, yes.
Might be a little too fast for me on this. What exactly were you looking for when we were on class? What answer did we
Okay. Are you guys cool with what we talked about here? You can see if I go and is everybody cool when I said this was y equals x, this path? Somebody with me? Alright, now, if you're cool with that fact, instead of calculating all the outputs, I could just literally let y equal x and do the same thing without making a bunch of points. Yeah, then I can calculate the limit directly. If y equals x, then I just need x to go to 0, which means y goes to 0.
So like the question says find two paths where the
Yes.
is undefined. And
You just have to keep trying some stuff until you get two paths that don't agree. Yeah, does it make sense? Okay, maybe. So let me just cut to the chase. One thing to notice about this, which power is off from the other ones? Y to the fourth. Yes? If you so what would you let x equal so that the bottom becomes becomes like terms? I want the bottom to become like terms. You could do this.
Why?
If I let x equal y, is the bottom like terms? If I let x equal y squared, isn't the bottom like terms? So and what is x equals y squared? What kind of path is that? Parabolic in which way? There it is, I like it. All I need is I just need somebody to kind of do this and then you got it. Alright, let me stop for a minute. So again, if you are 0, 0, and I want to know what my function's doing, I can come at you in all these different ways. The minute I start to walk a trajectory towards you, isn't that a function in the xy plane? So if I go straight at you, that could be y equals 3x, yes? If I go like this, that could be y equals x squared, yes? If I go this way, or something, that could be x equals y squared, yes? So instead of making a grid for every function, which will drive me insane, it almost doesn't matter if you guys, I'm cool with that, no. We want to do this a little bit better. So let me cut to the chase. We just figured out, if we let's try to do x equals y squared. I could put an m in front, but let's just do x equals y squared. So now it's going to be a function of y, correct? So the limit is y goes to 0. Because if y goes to 0, what does x do? Goes to 0. So does that follow what the problem wants me to do? Yes. It wants both of those to go to 0. If I do this, they'll both go to 0, correct? Sorry?
Nothing.
Oh. So now if I replace my x's with y squares, by the way, just to let you know, I always try to discuss things on a conversational level, try to have you guys see it's not as hard as it seems. This is weird. I need you to understand that I am aware that this is weird. I don't want you to think it's just weird to me. Listen to this guy. It's not supposed to be weird. No, this is supposed to be weird. But in trying to show you the math involved is not difficult. And the grid idea, I'm hoping, will help you see what we're actually doing theoretically instead of like concretely with this grid of numbers. Okay. By the way, real quick. Could you do a parabolic approach in this grid of numbers easy? What if that was the only way to make the answer different? Screw that way. Okay. So what do I get here? I get,
y4 over 2y4.
and then what happens here?
Cancel.
Yeah, these cancel, and I get 1/2. Did I find two paths that have different outputs? Different limits, I should say. Yes. Just like visually when one path was up on the upper trough and the other path was on the lower trough. So the twain shall never meet. Yes.
So, well, like, we're basically just trying to find a way to get it to simplify down. Like, looking at the homework,
I love it.
we're just.
There's a concept involved about approaching it, but when you get down to the actual nitty-gritty, you're trying to figure out, like, well, what did we just do? I try to show you something that will help you on a decent number of problems is,
Yeah.
well, what do I let one variable equal so it's like terms with the other one? Did you see what like terms did for us? All the shit canceled at the end. I got a number, and it was a number different from the one we just got, which means I'm done. What does it mean? What did we just do? What did we just show?
Proved it was continuous at 0.
Try again, say again. Prove that the limit does not exist, which means it's discontinuous. I love it. We haven't even talked about continuity. We're getting there. Yeah. Okay. So in general, I'm not going to say there won't be some in the homework where you have to make it a cube. Do you guys understand if you saw a x squared and a y to the 6th, you should probably let x equal y cubed? Does that make sense? So it could be anything, but it should be kind of obvious on a decent number of problems what to let something equal. So always try like y equals mx, or even start with y equals 0, x equals 0, right? And then go to y equals x cubed, or x equals y cubed, or whatever makes the powers kind of agree. Does that make sense? So that's a very nuts and bolts approach. So once we talk about the concept, you can get down to the what the hell am I actually going to do, right? Okay, I like it. So, somebody's gonna crack it open and hold it. Like, I need this. Okay. Where have I put those? So I have a handout here. Yay. That I want you guys to try a few things. You can try the 14.2 one first if you want to, because that's the stuff we just talked about. There's a problem on here from like domains and stuff. I did that. I love it. It's the best part of my job. Passing out. The best part of my job is passing out. So guys, I want you to try, and feel free to work with people near you if you want to. If you don't trust them, then just stay away from them. Number one is the domain and stuff, and I can't remember if I said the word contour map, but when we did, do you guys remember when we did the several K's? We like K equals 0 and K equals 1. Yes, you remember doing that?
Yeah.
That was a contour map. So a contour map is if I take the function and I smush it into, nobody's opened the pop-up book yet, right? And those circles I'm drawing are just what would be equal heights if I did let it pop out. You with me? So that's what a contour map is, showing several level curves. So when you draw a level curve, you put next to it what K is. If you want to, you can start with these. I started off, try this. I'm not going to say a word. see if you guys remember. When I give you a limit to try, there's something. What'd you guys get for A? Yeah, 1, 0, there's no issues. This is just polynomial in X and Y. Polynomial means it has no issues, yes? So if you just plug a 1 in for X and a 0 in for Y, you get 5 plus 1, 6. This one, when you see 0, 0, your brain clicks, but 0, 0 is not an issue, is it? The bottom is not 0. It cannot be indeterminate. It's not 0 or infinity. On the bottom you get, and on the top you get 0. They're both 0, so you get 0 minus 0, 0. And of course that is 0. Is that cool? So remember, something I hope your calculus teacher made clear is whenever I give you a limit problem, very first thing you do is, can I just throw the numbers in? If you can't, if you get indeterminate, then you do weird shit. You do L'Hopital's, you do factoring, you do paths, you go crazy. Is that okay? Does that sound familiar? And then this one,
The middle thing cancels. I don't know how to break the same thing.
Jeff. Hey, it's a 1. Okay. Take a 3 out. Dear God, if anybody just can't. Oh boy, it's going to be a problem. So the top factors like. Yes? So then these cancel. And then you can plug a 3, 1 because you killed the prop. So now I can plug a 3, 1 in. I can plug a 3 in and a 1 in. I get 3 times 6. 18! Bros are on fire. Cool. Yeah. So if you've taken me before, you know this. I'm going to give you at least one problem where the limit is you just plug the numbers in, you're done. Yes? Or you've got a factor. If factoring is an issue, that is an issue. That is a huge issue. Holy shit. Factoring is like the cornerstone. So trust me, if you have any issues with factoring, you're going to dislike the next test. Yes. So you work on it, is my thing.
Before you said all of the thing about L'Hopital, I did the L'Hopital and I got 18 as well.
So how'd you do L'Hopital's?
Just take derivative of the upper, take derivative of the bottom.
With respect to what?
Plug in values.
What'd you take the derivative with respect to?
Nothing.
That's impossible.
I just got
But do you see my point?
I do.
So this is a very simple function. You could kind of like bumble your way into the right answer. But do you understand how there's an issue there? It has to be d by d something. And you can't take a derivative of 2 parts of something with respect to something else entirely, yes? So we're getting to the point where we can kind of extend the idea of L'Hopital's into 2 dimensions. Simple function though, so it should come out the same. You guys kind of with me? There's an issue there. And this is the part we forget. This is why the prime notation is not as good as the d by dx notation. Because if I say d by dy, I know y is a variable. D by dx, I know x is a variable, yeah? Prime, no, it's just whatever variable's there, Okay. And now we have more than one variable there, that sucks. Okay. Sorry, did anybody do this already? I'm sorry. I thought everybody was going to start here, so I just kind of went there. You guys do this yet? Go for it. Or you could do, did they give you one of these? Yes, on the back are some path ones. So I'll leave it up to you what you want to try next. Maybe try the path ones next. Can everybody? Let's take a look. Now guys, real quick, I always like to remind students, how long have you been working with this idea? That long, yeah? So get off your back if you're like, you're not supposed to be sharp with this shit. You just learned this stuff, right? Okay, just, I'm hearing some people getting a little down themselves and like, no. This is brand new shit. This is really new shit. And it's weird shit, yes? Okay. So give yourself a chance to work with this. Did anybody get, what's one path you guys tried for part A? Y equals X? Okay. And if you follow that down, where'd you put your here? Y equals X. You could actually do either letter here you want to, but I'm gonna replace all my Y's with X. Is that cool? This is the x squared minus x squared over x squared plus x squared, which of course is 0. Is that cool? Even though you can't read that, sorry. Is that alright? By itself, it just means if I had the grid and I went at a diagonal, they would be approaching 0. That's all we know so far. Now I need an entirely different path. Now since you chose y equals x, it could be true that y equals 3x. 3x, Jeff? Yes, 3x. Could be different. I don't know, did somebody try mx or something? Did you try mx?
Yeah,
How'd it come out?
just 1 minus m squared over 1 plus m squared.
Okay, let's look at it. So if I try y equal mx, now replace y with mx. Is that okay? You see all the x's cancel, yes? So I get 1 minus m squared, I think, which is what you just said, yes? Now, real quick. This is a beautiful, I need you to see how it's really good. I tell people to start with y equals 0, x equals 0, because that's the quickest way to do this shit, yes? But then go to y equals mx. One reason you want to do mx instead of just 2x or 3x is because, do you see how that result is dependent on m? If I would have just done that from the beginning, didn't I already get infinite paths with different answers? What if m is 1? Then I recover this, yes? If m is 1, don't I get 0?
Yes.
What if m is 2? So if y equals 2x, what's the limit? 1 minus 4 over 1 plus 4. I get negative 3/5 and I'm done. Did I get 2 paths? I need you to let me try this again. Try y equals 0, x equals 0. Because that's quick as shit, yes? Did anybody try those? Alright, let's hear for you. Instead of doing y equals x, or y equals 2x, or y equals 3x, do y equals mx. Because your answer might depend on m, which means you're done. Because if you pick a different value for m, which means a different slope for your path, you get a different answer than another value of that. Does that make any sense? What is my goal here? I want to pick some y as a function of x or x as a function of y that represents my path as I try to approach 0, 0. Yes? Because the whole idea is I got to approach my input point from different directions and see if the limits don't agree. And in this problem, I already told you they don't. So you know there's going to be a path somewhere that's different from another path. Yes? If my result is dependent on m, that represents an infinite number of paths, because how many options did I have for m? Infinite. So every value of m I could pick is already a different path with a different answer. Does that make any sense? My whole point is to get a different output for a path. So it might be a good idea just to start with y equals mx. I always do 0 because it's just quick. And y equals 0 and x equals 0 could actually lead to different things. In fact, they do. So this is a perfect example. If y equals 0, here, Jeff, you got several of these, dude. If y equals 0, what does that lead to?
X squared over x squared.
So I get 1. If x equals 0, negative y squared over y squared. Negative 1. Done. I'm done. That's one reason why I do this, because they're quick and they could be done at the end. If those two agree, I do y equals mx. Because then maybe it's dependent on m, and I'm really dumb. Yes? Maybe? True, Jeff? Yes?
That's not always true.
Hell no. But that is the approach. That is the kind of. You guys need, you should by this point, when you get a certain kind of problem, you have kind of things you throw at it. You should have that happen. You should have done that sometime in your career. I'm telling you, when I ask you this kind of question, find two paths that lead to different results showing the limit does not exist. When I say that, this is what I try. X equals 0, y equals 0. Sometimes they'll be the same. Then you go, damn. Y equals mx. That might be the same as those. You go, shit. Then you go to y equals mx squared. That might be the same. You go, shit. Then you go to x equals my squared. You guys kind of with me? Now, just to really make sure you understand. On part B, what is it about the powers that tell me a good thing to try for a path? Y equals mx squared. Why? Because that would make the powers agree, yes? That would make it like terms, yes? You guys kind of with me? So if on the bottom it said x to the 6th plus y squared, I want to make y equal mx cubed. This is like I said earlier, are you with me? So there's only a finite number of paths for any given problem that you need to try. I need you to really understand this. So you don't envision yourself going, that didn't work, 10 minutes left in the test and you've only done this one problem. That didn't work, I've done 28 of these. No. It should be y equals 0, m equals 0, x equals 0, y equals mx, or y equals mx to the power that makes things happen, yes? So in part B, what did somebody try?
Zeros, but they both become.
You tried zeros? Yeah, so if you make zeros, they both become zero. So if you try x equals 0, y equals 0, these both lead to the limit equaling 0. Is that cool? Because the top is x squared y, so of course you get 0 over who cares? Yes? No? Is that okay? Okay. What else did we try?
Y equals mx squared.
Yes, because of this situation, yes? So if I let that happen, is everybody cool with how I'm changing this limit? You guys see that? Because now the variable I'm going to left with is x, and if x does this, y also does this, and therefore I'm fulfilling the requirements of the problem. Do you guys see that? Yes.
Wait, the limit is y goes to 0 is not 0, it's infinity.
No. The top, no, okay, let's do it. Okay. Real quick. If I let y equal 0, yes?
Yeah.
Okay. I'm going to get, if y equals 0, I'm letting x go to 0 because y already is there. Yes? Okay. So on the top I get 0. Is that cool?
Yeah.
Good? Because it's 2x squared times 0. And on the bottom I get x to the 4th. Yes?
Okay, yes.
That is always what? 0. So this is the cool thing. This is a very quick little side note, but this does confuse some people. And if it doesn't, I might confuse you right now, but oh well. If I let x go to 0, somebody might say, well, now that's indeterminate. But that is not true. The top is 0. Therefore, this is always 0. Yes? What is the one time this might not be 0 is when x is 0, and is x ever 0? Ah, there you go. Answer 0. So I've seen people get tripped up about that, and I understand the logic of what's tripping you up. It actually makes sense, but that's the little thing about it. I'm not letting x go to 0, so that's just always 0. Cool. Okay, I like it. So if I let y equal mx squared, I'll get 2x squared mx squared over x to the 4th plus m squared x squared. I have no idea why it was so. Sorry.
Would it be x to the 4th?
Oh, squared. I left off the square.
No, wait, wouldn't the m just not be the, you wouldn't have the square for the m?
Oh yeah, I kind of did one and not the other one. I'm with it. So then we get 2m squared x to the 4th over x to the 4th plus m squared x to the 4th. Okay, let me stop for a minute.
Wait, why is the,
I don't know.
why is the m squared?
Why is the which one squared?
Wouldn't it just, since the y you at the
M
top,
is squared here, and
Yeah,
M is
it-
squared here.
it shouldn't, the M squared there shouldn't happen because the Y on top is, it's just.
Oh, it's not
constant.
squared. Oh,
That's
so
why it's
good.
wrong.
Alright, thank you. I'll get there eventually. X goes to 0, 2, m x to the 4th over x to the 4th plus m squared x to the 4th. Okay. Thank you, Zach. And then what happens here?
Becomes 2,
Yeah, all the x to the 4ths cancel, so you get 2m over 1 plus m squared. Yes?
Yeah. You get-
Which some of you guys might realize, some of you guys might just go ahead and try mx and mx squared, because if you get a resultant dependent on m, like we said earlier, you're done. Now just pick two values of m.
1, 2.
In this case, I just need one, because we already got a limit of 0, didn't we? Now I just need a value of m that makes the limit not 0. So if I make 1, then my limit is 1. Yes? Yes?
So on an exam, you'll just pick any value for n, like at the end, plug it in.
If you get a limit that's
Yeah.
dependent on m, you just have to pick two values of m and you found two different outputs. Yes? In this case, we already got one limit of 0. So if we make m1, this is 1, two different limits along two different paths. Kick ass. Okay. So just to really put a bow on this, in 2D, I need two different paths. There are always only two paths I can go to approach something, yes? This side and this side. 3D, infinite paths. Right? So that's like a major upscale of complexity. You with me? But again, I'm never going to give you a problem where you have to try more than like 4 or 5 things. If I were me, I would try the zeros first. Some of you guys might see that mx and mx squared, that kind of thing might be a good thing to try first. Because then you get something dependent on m. Yes? Real quick, if we had not done these, and I only did this, I didn't do those, I only did this, I let m equal 1, I get a limit of 1, I let m equal 0, I get a limit of 0, I'm done. With only one thing of work. Does everybody see that?
Technically, doing m equals 0, you are doing y equals 0.
True. But it matches the y equals mx squared form. Okay. You guys all right? How do you feel? How much do you understand this now versus when you first came in the room? About an infinite percentage more. Yes? How many of you feel comfortable with this? Okay, cool. A few of you guys. That's good. That's better than I thought. Rory's letting me know very emphatically how he feels. Okay. Which means he could be saying he's great. So what about this one? How do I get this started? Yeah, the function I've got is basically a square root, which means the inside has to be
Greater than 0.
greater than equal to 0. So that means x squared plus y squared has to be greater than equal to 4. Now real quick. Can somebody give me a value for x squared plus y squared that would make that a true statement? X squared plus y squared is a number, correct? I just don't know what number because nobody told me what x and y are. Can you give me a number for x squared plus y squared that would make that a true statement? Don't overthink it. Give me a number to put in place of x squared plus y squared. 5. You guys see that? If I replace x squared plus y squared, if I make it equal to 5, that works, correct? Isn't that a circle of radius square root of 5? Isn't that a circle of radius bigger than 2?
Yeah.
Isn't the answer all the circles that have a radius bigger than 2? The shortcut for that is draw the circle of radius 2 and then shade everything outside of it. Yes? If it was less than or equal to, it would be contained in the circle. Greater than or equal to means it's outside the circle. Do you include the points on the circle? Yes, because it's allowed to equal to it. So your answer to these, I appreciate somebody in the back who just about drove themselves crazy, trying to figure out how to, you can make a little sun, trying to figure out how to write this x element of or whatever. Don't do that to yourself, holy shit. Just,
Except for getting all points that are not included.
if y is 0, so I'm here, yes? What can x be? Bigger than 2 or less than negative 2, correct? What if y is 2? What can x be? Anything. So there's no good way to write the domain by separating what x can be and what y can be, because they're dependent on each other. Yes? What's the best way to answer the question? Draw the picture. Do the work, draw the picture. Okay. You guys wish me? So what does it mean the graph of this should look like? Give me any true statement about the graph of this. No.
It's an empty. The circle-
Whatever the outputs do.
It's like an empty cup.
No, it's
Okay.
like everything's full of.
Can any output go over the origin? Because anything in that circle cannot have an output, correct? You with me? So here's what it looks like. Come back. Oh, you're there. You're not there. You're not there. There. Okay. Do you see how there's the domain? And there's no part of this that's over that part. Okay? The domain, of course, being everything outside the circle. Does this have an output? Yes. Does this have an output? No. Is that okay? Screw you, Jeff. You suck, Jeff. Okay. I'm sorry. Bless you. Oh yeah. Look at that. Oh, sorry. Sorry. Just playing around. This we're gonna get to. Yeah. Okay. And then this guy, draw a contour map. Can somebody tell me what's the first step in doing this?
You make
Shape.
x, y.
Yeah, I want the height to be a constant, correct? So I'm going to let this be k. And of course I'm going to square it to start to solve this. Yes? So I get x squared plus y squared equals k squared plus 4. Now, very quickly, if this is k, what's the smallest k could be?
0.
Because it's equal to a square root. The smallest the square root can be is 0, because I'm not considering complex numbers and blah, blah, blah. Yes? So I put a k equals 0, and what do I get? 4 equals x squared plus y squared, which is the level curve in the xy plane itself. As I move up, what's going to happen to my radius? Remember what it looked like. My radius has to get bigger because I can't go back in. Or at the very least, it's got to stay the same. But we know it gets bigger. And here, so if k equals 0, I get a circle of radius 2. What's a good thing to choose for k? Because we're doing this shit. We can be nice to ourselves. Square root of 5. If k is square root of 5, what do I get? Square root of 5 squared is 5 plus 4 is 9. So I get a radius 3 circle. So when I go to graph these, I make a radius 2 circle, 2, 2, negative 2, negative 2. And I put a little k equals 0, and then I make a radius 3 circle, 3, 3, blah, 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 and next to it I put k equals square root of 5. And I'll tell you how many to do, because how many of them are there? Because for every slice, I get another cross-section, yes? So you only have to do certain ones, and you can be nice to yourselves and pick good values of k.
Why is square root 5 a nice number?
Oh, if I have x squared plus y squared equals something, what do I want to be true about this to make the circle nice? X squared plus y squared equals 9 is good. Why? Because the radius is 3. So I want k squared plus 4 to be a square. If I make k 0, I get a square number, yes? If I make k 1, I get 5. That kind of sucks to graph. So I want k squared to be something that when I add it to 4, I get the next square number. The next square number is 9 above 4, right? So I want k to be square root of 5, so then I get 5 plus 4 is 9. What's another good value for k if I needed one more? 12. Square root of 12? Yes? So we make k square root of 12. Square root of 12 squared is 12 plus 4 is 16. That's a nice number that works well with circles. Yes?
Root 21, root 45, all those ones that will add up to be.
That's 4 off from a perfect square.
Yes, anything that's 4 off first.
Kick ass. Okay. Now, now we get into, any questions from that? I think we finished all of it, yes? Yes. Oh, by the way, don't worry excessively much about this. There might be one or two problems in there, but do you guys remember squeeze theorem?
Yeah.
That's perfectly answered. Yeah. So, if I wanted to investigate this limit, I want to investigate this limit. Real quick. Now this is where it gets a little bit tricky, because with the squeeze theorems we've done before, if I saw a sign inside of my function, what sign lived between? What value? Negative 1 and 1, right? So then that kind of sets up the inequality for me. This one, let's see if you guys get this. If I take the y out of here, I get this. Yes? If y is 0, isn't that 1? Yes?
Yes.
And that's the smallest I can get. I'm sorry, the largest. If I make y anything other than 0, won't I get something smaller than 1? Because now I'm making the bottom bigger. For some value of x. Are you guys kind of with me? Whatever x is, if I make y 0, I let this be the biggest it could be. Because when I divide by less, the output is bigger. That's it, right? If I make y anything other than 0, it's going to come out to be less than 1, correct? What? Give me an x. Give me a number. 2. 2 squared is 4 over 4. If I make that 0, isn't that 1? 4 over 4. If I make that 1, is 4 over 5. Is that smaller than 1? Yes. So the biggest this could be is 1. And that's by making y 0. The minute y is anything other than 0, I'm dividing by more than this guy is. I'm getting something smaller than 1. So have I bounded a part of my problem? Yes. Now, if I multiply by effectively y, now very quickly, we're not going to do a bunch of these problems because they get a little tricky. If y is negative, wouldn't the inequalities switch? But wouldn't it be effectively the same expression? So that's why I put absolute value, because it doesn't matter if it's positive or negative, it's going to be the same expression. Yes, maybe? So what I want to do with squeeze theorem is to have the function I'm working with caught between two values. And then if I take the limit of all sides, if these two agree, that forces the middle one to be the same thing. So if you wanted to prove something actually had a limit, you could go insane checking every possible path to make sure they're all the same. Because how many paths are there? Infinite. So squeeze theorem gives us a way to stave off a decent chunk of insanity for a little while. Not all of it. You're going to go insane a little bit. Yes?
So is the reason we use y because it's the only variable without a power?
Good. In this case, it's because it doesn't have a squared on it. So if I leave it like that, then this is obviously less than or equal to 1. Okay. Maybe. Okay. I'm not going to give you a lot of squeeze theorem stuff, because in 3 dimensions it gets really even worse than 2D, and a lot of people don't like squeeze theorem, which is weird to me because, again, I'm a weird person, so it's okay. Okay. Do you guys want to take a break?
Yes.
What do we? Can we do 5 minutes? I'm going to do a little bit, and then I'll let us out early.
Okay.
All right, 5 minutes. Look at that, democracy in action. Little to do in so much time. Strike that, reverse it.
He plays that also perfectly.
I know. I met him. He was signing a book at Barnes & Noble, and I was the 432nd person to see it. He was very tired. All right. So, guys, last thing for today. 14.3. What I want us to do is, I think I said this earlier. I didn't want to do the grid earlier because we're going to do a grid now. So let's make a grid of values. I'm not doing a limit, by the way. I just want a grid of values, and I'll give you guys the inputs. Same idea as before. Start to fill it in, and then I'll catch y'all up. Just want you guys to try. Everybody got the function written down? I'm sorry. I'm trying to get all this in here at one time. The other way, Jeff.
How would you know when to use decimal values and when to use?
Oh, okay, real quick. I'm gonna investigate this guy's slope. So I'm not asking us to do a limit. So I was very vague about what I wanted us to do. I just basically want you to figure out what are the outputs given those inputs. It's like making an XY table for -1, negative, you know. What we're going to do is I'm gonna try to show you a really beautiful thing happens when we start trying to figure out what the slope of this is. Now we already talked about the fact, I can't just say the slope of this is 7, because it completely depends which way you try to go. Yes? In 2D, the slope is defined on moving in the positive x direction. In 3D, again, I've got multiple ways I can go. I've got an entire plane of shit I can move along. Okay. So let me catch up to you guys. What'd you guys get here? Anybody got this?
-10.
Yeah, -10.
-6.
-6 here. What, anybody get this one?
-1.
No.
-2.
I think it's -3, yes? Let's see. That would be -2 times 1 plus -1. So -3, yeah. So let me just fill this in. Yeah, that's easy. Do a couple of them, and just getting outputs for these things is really nice. So obviously I did this earlier. I'm not just doing that fast in my head. Okay. The whole idea of a derivative in 3D is I must talk about it from the standpoint of face a certain direction and move that way. What do I do? Yes? So I talked about the fact that I could look this way and there's an upslope, and I could look that way and there's a downslope. So the derivative this way is very different from the derivative that way. Yes?
Yeah.
This way is positive, that way is negative. I almost don't care what the number is. Obviously, they're different. What's really cool, can you guys tell me the slope if I hold y to be -2? Yeah. Can you guys see the slope? If I hold y to be -2, what's the slope? 4. You guys see it? You can't always make a grid and see the damn thing, but this is a relatively simple function. We can see it. So if I'm on the y-axis, you can do it, Jeff. If I'm on the y-axis at -2, and I move in the x direction, if I move in the positive x direction, I'm going to go up, yes? I'm climbing up out of the hole. So at first I'm at -10, at -2, -2. And if I move in the positive x direction, but I keep my y value the same, yes? Then I'm going to end up going up in that direction. I like it. So far so good. What if I hold y to be -1? So here, the slope as x changes is 4. What if you hold y at -1? Slope is 1. So I can have a function where it's, if I'm looking at it here, and if I just step over a little bit, it's like that. Yes? Here I'm going up a steep hill, and over here it's down a little bit. Now I got less of a steep hill. And you can imagine, if you've walked around parts of San Diego, Mission Hills, whatever, you've experienced this directly. You're walking like, let me go that way. No, let me not go that way. No? Have you guys been to those really steep hills?
Yeah.
You know what I'm talking about? Yes? I'm like, do I want to work out or no? Somebody's sort of with me so far. This is kind of beautiful. You can actually see, if I hold y to be -1 and I let x change, I can see the slope is 1. If I hold y to be 0, I see the slope is 0. Yes. Now, what if I hold x constant? Is it as easy?
No.
No! Okay, so if I hold x to be -2, what does the slope start off at? And you can't tell me precisely what it is, because as you know from calculus, the minute you move away from a point, your slope is different. So don't tell me it's 7, but at least you can tell me it's kind of big positive, yes? Because it went from down -10 to -3, so I feel like the slope at -2 is big positive, yes?
Yeah.
What happens from -1 to 0? The slope is now still positive, but not as big. Or he's like, I'm going to be right. One more time. After I go from 0 to 1, what happens? Yeah. Sort of. Not perfectly, right? Then it becomes negative, and then it becomes big negative, correct?
Yep.
Are you guys with me?
Yeah.
So listen. When we held y constant, the slope was independent of x. Let me say this. You guys see what I mean? If I hold y constant, you all agree with me that the slope did not give the first shit what x was. It's 4, 4, 4. Do you see that? But if I hold x constant, does the slope only depend on y? No, it's different as they move along. It starts off big positive, 0, then it's negative. It kind of depends on what the value of y is. Do you see what I mean? When I'm here, it's big positive. When I'm here, it's big negative. So it depends on the value of y. Is everybody with me? So it seems that if I hold y constant, the slope is constant. It's independent of x. But if I hold x constant, the slope changes. It's dependent on y. Does everybody kind of see what I just said? You could see it beautifully in this grid. So, now you're all saying, Jeff, derivatives were so easy. Don't mess up my derivatives, man. I've already got integrals, and they suck. So, here's the nice thing. The way that these work, just to kind of cut to the chase a little bit, and then I'll come in with the, what do you call it, legalese, the formal approach in a second. If I look at this, and just to show you some notation, I'm not going to take a total derivative. I'm going to take a partial derivative. So that's the difference. I'm going to take a partial derivative. Let's do it with respect to x. Which means, when I say that, I am holding y constant, just like we did first thing. If I hold y constant, what does the slope do? So, x is the variable. Everything else in there is a number. So what is the derivative of xy squared?
Y squared.
Y squared. What's the derivative of 5x?
5.
With respect to x, 5. What's the derivative of 6x?
6.
So it's the derivative of y squared x with respect to x. Y squared. Y squared is a number. We're holding it constant. It's just like 5. This is not as bad as implicit at all. This is nowhere. You guys remember implicit differentiation? Some of you guys have blocked that out of your memory, and some of you guys are like, why did you bring that up? This is so much better than that. What's the derivative of y then?
0.
0, because it's a constant, isn't it? Now, real quick, what did I say? If I hold y constant, like we just did, didn't we? What did I say was allowed to change? X, which is effectively me saying y is constant. Did the slope change as I moved along? Slope is constant. It didn't care what the x value was. And in fact, look, our partial, does it depend on x? No. In fact, if y is -2, what did you guys say the slope was? If y is -2, what's this? Frickin' 4. You guys kind of with me? Do you guys see that? Okay. So what about this? Do you see how I'm making my d's, by the way? Do you see how they're They're not really complete, which is nice because it's sort of partial derivatives, so you don't make a complete D. It's kind of like bent over a little bit. It's like, oh, good. No. So when you do, if you do a real D, that means total derivative. When you do a little cursive looking D, a little incomplete D, you didn't come back down, that's partial derivative. So partially make a D when you want to do partial derivatives. You guys kind of with me? There is better notation I'm going to show you in a minute, but I want to start with this notation. This is slightly better notation than what I'm about to show you. What is df dy? So what am I holding constant now? X. X is a number. So what's the derivative of number y squared?
2x.
2x y. And what's the derivative of y? 1. How does that line up with what we said earlier? As I moved along, held x constant, didn't the slope change depending on where I was on the y?
Yeah.
Isn't this dependent on both x and y? So if I hold x constant, it's dependent on y still. That's why it changed. It wasn't the same all the way through. The slope was not constant, and I can see that in the partial that we just did. Okay, maybe. So, what is the derivative? What is the partial derivative in the y direction at the point -2, -2?
Negative 1. No.
So it'd be 2 times -2 times -2, yes? So it's 8 plus 1, 9. And didn't we say we thought it was pretty decently big positive? It's bigger than 7 because, again, right here it's 9. The minute I start to move away from that, it's smaller. So the averaging effect is it looks like it went up by 7, yes? But the slope at this point, hello, next room, the slope at this point is 9. But the minute I move away from it, it's not as big of a slope anymore. That's why I didn't get all the way to -1. Yes, sir.
Can we check what is it for the -1 and averaging?
Where are we at? Oh, let's try. What is the, let me put somewhere, what is the slope at the point -2, -1? I'm running out of room here. df dy at -2, -1. That's 5, right?
Yeah.
Yeah, okay. If you average out 9 and 5, you get
Exactly.
not the right thing. Yeah, because, again, slope isn't linear between those 2 points. It's dependent on x times y, which is not linear, yes? Okay, okay. I guess, does that, alright, real quick. A little bit weird, but you told me exactly what the shit was going on. You could see it. And this way you knew was stranger. This way was easy. This way was weirder, yes? And we see that. Easy, because it only cares about y. Harder, because it cares about both. Okay. Damn it. So part of this is going to be just straight up, can you do partial derivatives? You've done very little, but can you see how they're relatively easy? If you can do derivatives, you can do partial derivatives. Easy. And before I let you out, here's the shorthand notation. Instead of saying df dx, we say f little x.
What do you mean by not complete
df.
So this is a complete D, yes? Do you see how I came back down?
Okay.
This, I didn't come back down. I don't know, I'm just trying to make it make sense as to why the symbol is that. To me, I always saw it as not a complete letter D.
So is that a lowercase f or an uppercase f?
That is a lowercase f.
Lowercase.
Yeah. Uppercase F doesn't go through. And they used to do this, kids, right?
Hey.
Thanks, guy. So what would df dy be?
F at y.
Some crazy shit. What about second partial? What do you think?
y2.
Fyy. So what about the 18th partial? Fyy. Oh God. Alright. That's why the little subscript y, if you're going to do multiple levels of derivatives, you don't use that notation, because that would drive everybody. Fy, xxy, yy, xy. No, God, no. Maybe? You guys kind of. Alright, so this is nice. We're still in 3D, so that kind of sucks. It's too bad. But we're getting into derivatives. Derivatives are always nicer. Partials are a little bit worse, but they're not as bad as you might have thought they were going to be, is my hope. So next time we'll get a little deeper. I've got a handout for you guys to try some concrete examples. Then we got to talk about the interpretation of our answers. Yes, that's the next level. We're getting into 3 for sure. Yeah. We don't do 2-5. That's not in our curriculum yet. 2-5 out. On the homework sheet, there should be nothing.
So I can just read 3.
That's always your own call.
Yeah.
Like I like this college, so you know. So you could.
No, I'm just